When you push up a single fader on a digital console and pass a pristine audio signal through it, the result is almost always flawless. One microphone sounds exactly like one microphone. But modern production does not exist in a vacuum of single channels. A standard live show or large-scale broadcast routinely combines 40, 60, or even 80 active sources simultaneously. This technical specification sheet details the dMix system. It outlines performance metrics down to fractions of a unit: total harmonic distortion at 0.001%, latency at 0.3 milliseconds, dynamic range at 115 decibels. It is common industry practice to dismiss microscopic differences in these numbers as purely laboratory data. The assumption is that fractions of a millisecond or thousandths of a percent cannot possibly affect the human ear during a live performance. That assumption fails to account for the physical reality of a cumulative summing matrix. When dozens of complex signals are combined, these tiny fractions mathematically dictate phase coherence across speaker arrays, the buildup of harmonic congestion in the mid-range, and the hard physical limits of gain before feedback. A mixing console's actual performance profile remains hidden on a single channel. It is only fully revealed when its hardware is forced to process the unforgiving mathematics of massive channel summing. Consider a basic test tone, a 1 kHz fundamental sine wave passing through a single channel. This spectrum analyzer shows what happens to that signal. Total harmonic distortion is the generation of new, unoriginal tones, distinct from broadband noise. Alongside the 1 kHz fundamental spike, the circuit creates these smaller harmonic products at 2, 3, and 4 kHz. We can compare how two different systems handle this exact same tone. On the left is a standard channel operating with 0.005% THD. On the right is the dMix architecture, operating at 0.001% THD. The visual gap between these two harmonic noise floors is a 14 decibel difference. The standard channel places its harmonic artifacts at -86 dB relative to the carrier, while the dMix channel pushes them down to -100 dB. Now, apply the mechanics of digital summing. If we take 10 channels carrying similar spectral energy and route them to a single stereo bus, the signals merge. As the main 1 kHz fundamental spikes add together and grow larger, the coherent harmonic distortion spikes grow perfectly in step with them. This rising accumulation of unoriginal tones creates a harmonic shadow. It tracks the source material exactly, adding artificial content to the mix. If a system starts with a higher THD percentage, this harmonic shadow is pushed aggressively upward into the audible mid-range. It quickly consumes the acoustic space where vocals and acoustic instruments are supposed to sit. Starting with an ultra-low, -100 decibel THD floor is the physical mechanism that keeps this shadow buried. It is the only mathematical way to keep an 80-channel mix from turning brittle and congested. While harmonic distortion dictates the frequency domain of a mix, system clarity is equally governed by the time domain. Processing time through a console is measured as latency. At audio frequencies, sub-millisecond console latency behaves as a critical phase shift variable. This graph plots two identical 1 kHz sine waves. If we compare a standard console operating at 0.7 milliseconds of latency against the dMix operating at 0.3 milliseconds, we generate a time delta of exactly 0.4 milliseconds between the two waves. At 1 kHz, that 0.4 millisecond delay translates into a massive 144-degree phase shift. The peaks of the waveforms are now fighting each other. We can map this time delta directly to physical space. Sound travels through air at a constant speed, meaning a 0.4 millisecond delay is physically identical to moving a speaker 13.7 centimeters away. When you deploy multi-speaker arrays, stage wedges, and in-ear monitors, this localized phase shift moves the cancellation points across the stage. A singer feels the physical vibration of their own voice out of sync with the electronic feed arriving in their ears. Reducing internal latency to the absolute minimum is required to lock these signals back together. It preserves the exact spatial alignment between the immediate acoustic energy on stage and the reinforced sound coming out of the PA. This precise timing alignment governs the physical stability of the stage environment. Feedback is a mechanical loop defined by timing and phase. This block diagram illustrates the closed loop of a standard stage monitor. Sound leaves the floor wedge, travels roughly 1.5 meters through the air, enters the vocal microphone, passes through the console, and returns out of the wedge. The physical air travel across that 1.5 meter gap takes precisely 4.37 milliseconds. The mixing console acts as an electronic extension of this physical space. It adds its processing latency directly to the air travel time. If we insert a typical console latency of 0.7 milliseconds, the total continuous loop takes 5.07 milliseconds. If we substitute the 0.3 millisecond dMix latency, the total loop drops to 4.67 milliseconds. This shift in total delay physically changes how the frequencies interact. As the timing drops to 4.67 milliseconds, the deep cancellation notches of the comb filtering effect slide horizontally into different frequency bands. Faster processing alters the mechanical resonance of the loop itself. It shifts volatile frequencies away from the microphone's natural tick-up characteristics, which increases overall acoustic stability. Engineering a faster signal path directly increases the usable gain before feedback. The monitor engineer achieves higher wedge volumes without relying on destructive equalization. Beyond precision timing, a large mix requires a wide operational window to absorb unpredictable, high-pressure live sources across dozens of open microphones. This decibel scale shows the operating window of the dMix system. The distance between the absolute noise floor at the bottom and the clipping point at the top measures exactly 115 decibels of dynamic range. The extreme peak of this scale marks a maximum input capacity of plus 28 dBu, giving the preamps a massive tolerance before clipping. At the other end of the signal path, the mix bus maintains a maximum output level of plus 24 dBu, preserving headroom at the summing stage. This ceiling is engineered to absorb instantaneous energy. When hot wireless receivers or aggressive snare drum hits hit the preamps, the signals peak safely below the threshold without overloading the input circuit. This wide capacity removes the need to run channel gain structures dangerously hot just to keep the audio above the internal noise floor. This dynamic capacity connects directly with the console's extended 96 kHz frequency response and tightly controlled sub-10-degree phase shift at 20 kHz, capturing the full depth of the audio. Generous analog headroom acts as a required buffer. It ensures that the accumulated noise of 80 open channels cannot aggregate and overwhelm the clarity of the mix. Optimizing a single specification in isolation will never guarantee a transparent mixing environment. A console built with exceptionally low THD but high latency will measure perfectly on a static test sheet. The signal is clean, but spatially disconnected and sluggish for the performer on stage. Conversely, a console built with extremely low latency but high THD will feel incredibly fast in the stage monitors, but the main mix will rapidly fill with harmonic congestion and muddy buildup as the channel count scales up. This schematic details the dMix architecture, a fully interdependent matrix. The audio path starts with 0.001% THD, feeds a 115 decibel pipeline, and exits a 0.3 millisecond output matrix. Passing 80 channels through this architecture eliminates harmonic buildup, preserves mathematical phase coherence, maximizes gain before feedback stability, and provides the engineer with a perfectly neutral tonal starting point. This precision engineering grants the operator the absolute freedom to mix the source material, rather than continuously fighting the limitations of the hardware. In high-stakes, large-format audio environments, the most effective mixing console uses applied mathematics to remove itself from the acoustic equation entirely.